Let us now discuss the single phase grid connection. As the PV module is being interfaced to a single phase grid. Let us first draw the topology of the PV module being connected to a single phase grid. The PV module, terminals being buffered, is connected to a single phase inverter, which is consisting of a bridge having 4 switches, full bridge having 4 switches, and from the center of this bridge arms we will connect it to a single phase transformer like this, and the secondary side of the transformer is connected to an inductor, and through the inductor is connected to the line neutral of the grid for single phase grid. So this is the basic topology of the single phase grid which we have discussed earlier. This PV and this is the inverter. Let us name these parts. Now the gate drive here, unlike the 3-phase case, we need to drive only 4 switches. So let us have 4 gate drives, and the signals for the gate drive are coming from a PWM module. The PWM module will give 2 signals depending upon the type of the PWM, which will be used for driving these 4 switches. Let us now sense the current that is flowing through the inductor into the grid, that we are pumping into the grid. We will call it as Ig. And let us also measure the phase voltage across line and neutral, and I will call that one as Vg, that is the grid voltage. Grid voltage Vg is Vm sin omega t. It of course contains a lot of harmonics, but let us say that Vg is Vm sin omega t, and Ig we want it to be Im sin omega t. That is, we would like to inject the current into the grid at unity power factor. So the moment you say this is Vm sin omega t, this is Im sin omega t, this is actually I beta, this is V beta. There is no V alpha or I alpha. So we have to generate it, we have to create the alpha component so that it will fit into the alpha beta coordinate axis. Let me consider a phase shifter block. So let us say this phase shifter block does the job of taking the input signal and shifting the phase by 90 degrees. We will see how we can realize that, but that is the objective of this phase shifter block. So to the input of the phase shifter block I will give Ig, which is considered as I beta because it is Im sin omega t, and the output of the phase shifter block will give you I alpha. So after this Im sin omega t is passed through the phase shifter block, it will become Im cos omega t shifted by 90 degrees. Now I have I alpha and I have I beta also, so which I can pass it to a transformation. This is alpha beta to dq, which will give me id and iq. So now I have this id and iq, which are DC quantities. Due to this alpha beta to dq transformation, there is a rho input which has to be given, so we will provide that rho input. Now what is that rho? Rho is the angle between the alpha beta coordinate axis and the dq coordinate axis. I will come to I'll come and discuss later on how we will generate this rho. Now that I have, let us say, id and iq, the DC quantities of the current, I will now have a control mechanism like this. So I have ID star, ID, just like in the case of three-phase, and the error is passed through a PI controller. Similarly, I will have another control mechanism for IQ star. IQ is fed back, and I will have a PI controller. So we'll see what we have to set for ID star and IQ star. ID is basically this transformed current which is given here. IQ is this transformed current which is given here, coming ultimately from an input measurement. Now this PI, these two PI outputs will be passed through a transformation. This PI controller outputs will represent voltages which need to be given to the PWM to control the inverter. So this will be a DQ to alpha beta transformation. It also needs rho information. Rho, which is the angle between the DQ axis and the alpha beta axis. The output of this will be V alpha star or reference, V beta star, and these two will act as a reference for the PWM generation. Means this will be given as the signal for comparing with a triangle and generate the pulses for giving it to the gate drive. Now we don't need to use both V alpha star and V beta star. See that Vg here is Vm sin omega t, which is V beta. Now Ig is also I beta, Vg is V beta, that is the beta axis components we have. We generated the alpha axis components by this phase shift. We generated I alpha, and then the ID and IQ were obtained. So we need to use only the beta axis components. The alpha axis components were created just to provide us the transformation so that we could go into the DQ domain, that is the DC domain, so that you could do set point control. So here we will use only one of this, which is V beta here for now, because we are taking this as Vm sin omega t, not Vm cos omega t. So we will use that. Now this will go to the PWM, it will generate the PWM signals, gate drive, and then it will drive the current, pump the current into the grid. Now this current Ig which is being pumped into the grid is the one which is actually being controlled, because these are current controllers and we are doing current control. We need to set these references. Before we set these references, let us see how we are going to get this row, these two rows. Let me use another phase shifter. The input to that is Vg, which is V beta, and I will use a alpha beta to DQ transformator. The phase shifter output is going to give me V alpha because it has shifted it by 90 degrees, which is Vm cos omega t. This was Vm sin omega t, and I can use Vg here. So this will give me V beta and V alpha, and I will pass it through alpha beta to DQ, which will give me Vd and Vq, and this will have a row input. So how do I get this row input? I will set up a control system here. I will have a reference, and the feedback point is VQ, the converted transformed VQ, the output of that, the error is given to a PI block. The output of the PI block is given as row to this alpha beta to DQ transformation, just like as we did in the three-phase system. Now this VQ star here, I am setting it to 0. Then eventually this control mechanism will operate in such a way that this PI controller, being a high gain controller, will make this error 0, which means VQ will become 0, match with the VQ star, and therefore we can say that the row is at such an angle that the DQ axis is aligned along the VD, which is the voltage space vector. So once it is aligned along VG, then I can set commands to the current set points or the current references. So I would not like to have any quadrature component of the current. I would like to inject only active current, which means in phase current. So therefore IQ has to be set to 0. There should not be any quadrature component. Then the current space phasor will become in line with the voltage space vector, which will be in line with the DQ axis of the rotating DQ axis coordinate system, just like in a three-phase system. So we will set IQ star to be 0, and ID star, whatever value that is being set here, will be the amplitude of the current that will be actually pumped in here, which is directly proportional to the power being pumped into the grid, because the voltage is fixed by the grid. So therefore ID star set point should actually have the output of the MPPT control algorithm. So therefore I will set up this MPPT block. Now this is VT, the terminal voltage of the PV. I'll measure also IT, the current through the PV. We will have a MPPT block. The inputs are VT and IT. Power will be calculated, and an MPPT algorithm can be used to obtain an output which will be proportional to IMPP, current at maximum power point, and that will be given as a set point to ID star. So output of the MPP will determine ID star, and ID will try to match that, meaning the current that is flowing here would correspond to the maximum power point of the PV panel, thereby achieving MPPT, integrated MPPT control and grid connection. So this would be the entire block diagram for a single phase grid connected inverter. Now what about these two phase shift blocks? How will you make the phase shift? I will just tell that right now. Let us now see how we obtain the 90-degree phase shift. So consider this graph where the x-axis is omega, frequency, not time. Now this graph has magnitude as the y-axis, and this graph has phase as the y-axis. Now consider a first order filter. Now first order filter will have a magnitude versus omega plot, something like this. This slope is minus 20 dB per decade, and find out the 3 dB point below the flat portion of the magnitude curve. That is 3 dB below the magnitude at omega, which is DC. So this is the 3 dB below point. Now at this point the gain is 0.707 with respect to the flat portion. Now take the frequency take this vertical line which cuts the frequency and look at the phase curve. The phase at that 3 dB point will be 45 degrees. So this 0 degree minus 45 degree, eventually this phase curve will reach 90 degree. So for us, the grid frequency is very stable. It varies between 49.5 to 50.5 hertz, which is a very small margin. It's more or less 50 hertz. So this line should be at frequency which is 50 hertz. Then we can say now at this point the gain is 0.707 with respect to omega at DC, or the flat portion of this magnitude curve. Now we can say that if I have this first order filter and at 50 hertz it is so designed that it is having a gain of 0.707 or an angle of 45 degrees, then I will use two such first order filters, each providing 45 degree angle. If I am biasing it in that fashion, designing it in that fashion where the 3 dB point is at 50 hertz, then this first order filter will give a gain of 0.707 and 45 degree shift. Another first order filter will give a gain of 0.707, 45 degree shift. Overall, I will have a 0.5, 0.707 into 0.707 will be 0.5 gain and a 90 degree shift. Now pass this through a gain block, gain of 2, and I will get 1 gain same as the input and with a 90 degree shift. So if I am having xm sine omega t waveform at the input, it will pass through, and at the output here you will get xm cos omega t. So this is how you will generate a 90 degree phase shift, the one that I had indicated here, this and this. So this entire single phase grid connected inverter topology can be implemented.